And then the other one has some like example problems.
Quick question.
Yeah.
You want to be on stage or on the floor today?
On the stage.
Yeah.
Does that make sense?
Yep. No PowerPoint.
No, we have papers.
That's great.
You know what it's about.
Yep. Right. I got the mics.
And the top and side doors going to be open.
Yes.
Does that make sense?
Well, the top won't be, but the side doors will be.
Well, we're going to have elementary teachers come in too. Does that make sense?
Yeah, they come through the box office doors, but I'll open the top ones anyways.
Yeah, because they might not know. You know what I mean? Like they may park in A lot, walk across the loop.
Yeah.
Like they're chained, right? Or not? Can you
we'll fix it.
Okay, that'd be cool. All right, and I'll be down I'll come down immediately, like 2:25. Does that make sense?
Good. Oh yeah.
Yeah. All right.
Sounds great. I'll see you
cool.
then.
Thank you so much. All right. What was I saying? Oh yeah. So there's a packet, and then there's like some problems that are good examples, and we'll do some of those example problems together, and then I got like more problem sets and stuff like that. So, all right. There's other gas laws besides Avogadro's law, the Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. One of the most important laws is a law called the ideal gas law. And it's not called the ideal gas law because it's like the best gas law, but there are real gases and ideal gases. And in the kinetic molecular theory of gases, there are some important postulates. And some of those postulates include that like when collisions happen between molecules, they're perfectly elastic collisions, that collisions happen between both the particles and the wall of the container, that no energy is lost in collisions. There's a bunch of different postulates, and those postulates are related to types of gases we call ideal gases. But for an ideal gas, there's an important relationship between the pressure, the volume, the temperature of the gas, and the quantity of gas in a container. So the ideal gas law refers to gases that are called ideal gases. So some things that you've got to be able to do. Let me make sure that's right. Yeah, like on the bottom, how to do some conversions. So in the ideal gas law, there are quantities of the mole, quantities in temperature, quantities in pressure, and you've got to be able to get into correct or standard units in order to get good results. Hold on, I gotta do something. Let's see, share screen, desktop 2. I always forget to do that. All right, so if you're remote, in the folder for this week, there's a thing that says ideal gas presentation, and this is in there. So first thing, like sometimes you have a quantity of gas that's in mass. So maybe I have 38 grams of hydrogen, and in the ideal gas law, there's a quantity in the equation that's a molar quantity. So to convert from grams to moles, you can just take the formula mass. So hydrogen is H2. It has a mass of around 2.02 grams per mole. So to convert from mass to moles, it's around 19. 38 divided by 2.02, 18.8 moles. And then also, because the ideal gas law could be used to figure out a mass, the ideal gas law will report values in the unit the mole. So maybe we find out that in a quantity of gas, we have like 4.7 moles of oxygen. Oxygen is O2. And you want to convert that into grams. You can put 1 mole in the denominator and the formula mass for oxygen in the numerator. And that's like 32.0 grams. So 4.7 times 32 is like 150 grams. So converting between grams and moles, you just use the formula mass on the periodic table. There's 2 papers there. Another thing to remember is what STP stands for. STP stands for standard temperature and pressure. Standard temperature, is 0 degrees Celsius, and that is the same then as 273 Kelvin. Standard pressure is 1 atmosphere, but 1 atmosphere is the same as 2 other standard unit quantities, 101.3 do we have 760 and 100? I forget which conversions. Yeah, 101.3 kilopascal or 760 millimeters of mercury. So there's only one condition for standard temperature, and it's 0 degrees Celsius, but that happens to be the same temperature as 273 Kelvin. Standard pressure is 1 atmosphere, but there are two other values depending upon what units you use in kilopascals and millimeters of mercury. It's like in some fields of science, everything is very well standardized, but in the study of gases, different people use gases for different things. In conventional talk about pressures, talking about pressures in atmospheres is useful to, if I'm like, oh yeah, I got this gas and it's 6 atmospheres of pressure, then it's 6 times atmospheric pressure. But this unit of kilopascal, well, if you convert this into unit, the pascal is actually the standard unit for pressure that's commonly used in units called MKS units, meter, kilogram, and seconds, that we use in physics. The unit, the millimeter of mercury, is a common unit that's used by meteorologists who study atmospheric pressure. To physical chemists, there's another pressure unit called the bar. We don't use bar in this class. There's lots of different ways to measure and express pressures. So the reason why there are different units and you got to be able to convert between them is because different fields of science use different units for different and important and good reasons. There's smart reasons to use different units. What's just kind of a bummer is you got to get familiar with all of them. So that's like a refresher, recall about some important basic stuff about converting between mass and moles and STP values. So for instance, you got a pressure 720 millimeters of mercury. We want to get that into the unit, the kilopascal. Well, the things that are true for pressure is that, I'll just write it up here like I just did. 1 atmosphere is the same as 760 millimeters of mercury. That's the same as 101.3 kilopascal. All these values are equivalent to each other. Same as saying like 12 is equal to a dozen. So if I want to convert millimeters of mercury into kilopascal, if I have 720 millimeters of mercury, and I want to convert into kilopascal, because all of these values are equivalent to each other, 760 millimeters of mercury is the same as 101.3 kilopascal. In a conversion factor, the values in the denominator are always equal to the values that are in the numerator. So I can write 101.3 kilopascal in the numerator. The value in the denominator and the value in the numerator, they're equivalent to each other. So really the conversion factor is equal to 101.3 divided by 760. So that's like, well, this has 3 significant figures, it turns out, the 760. So 96.0 is good. 96.0 kilopascal. You want to convert atmospheres into millimeters of mercury. So if I've got 1.2 atmospheres, an atmosphere is the same as 760 millimeters of mercury, and that's a definitional value, so it doesn't really have a significant digit or significant figure issue. It's like an infinite number of significant figures because we define it to be 1 atmosphere pressure, millimeters of mercury. So 1.2 times 760, 912 millimeters of mercury. But really, because the 1.2 atmospheres, which is a measurement, has only 2 significant figures, 91 millimeters of mercury is a good value. So the only thing I'm telling you this for, and this is nothing new, is that you might have to convert values from millimeters of mercury into kilopascals, kilopascals into atmospheres, atmospheres into millimeters of mercury. You got to get to be able to convert the values. You can use, for these 3 equivalent values, you can use any one of the 3 in the numerator of the conversion factor and any one of the 3 in the denominator of the conversion factor. Because with conversion factors, the numerators and denominators just have to be equal or equivalent to each other. Okay, so what is the ideal gas law? So the ideal gas law is written like this: PV equals nRT. And some people call it the Pivnert equation because it's like you could, if it's a word, it'd be like Pivnert. It's a way to remember it. Uh, P is capitalized, V is capitalized. They are for pressure and volume. Capital P is for pressure, capital V is for volume. V is a funny variable in physics and chemistry because capital V is also for voltage and lowercase v is for velocity. And there's a letter in the Greek alphabet, nu, which is used for frequency, which looks a lot like a lowercase v. But here, this is the volume. N, is the number of moles of like whatever. So of the gas. N stands for number of moles. And then R is called the ideal gas constant or the universal gas constant. You'll see it called the universal gas constant. You also see it called the ideal gas constant. And temperature, the thing about this temperature is it must be in Kelvin. It cannot be in Celsius. So the unit for pressure could be anything. The unit for pressure, it could be atmospheres, it could be millimeters of mercury, and it could be kilopascal. There are different values for the ideal gas constant. So here's what's important. This equation can be rewritten in the form, if you divide both sides by n and t, into a form that says R is equal to PV over NT. And the deal with that idea is that if R is a constant, it's some kind of a number that doesn't change, that the pressure times the volume divided by the number of moles and the temperature of any gas, no matter what, is always equal to some constant value. And because the ideal gas constant never changes, you could have a condition for a gas that constantly changes. So this could be a starting condition like P1 V1 over N1 T1 is equal to some constant, and the gas could change into some final condition, P2 V2 over N2 T2. And that looks a lot like the combined gas law, because the combined gas law, I'll just write it over here, combined gas law, is P1 V1 over T1 is equal to P2 V2 over T2. So what's different about the ideal gas law, if you talk about that the pressure times volume divided by number of moles and temperature is always equal to a fixed value or constant, that you can have a change for a gas going from condition 1 to condition 2. And this equation includes a number of moles, because the deal is, until now, when we use Boyle's law and Charles' law, the combined gas law, those don't describe situations where gas is being created out of liquids or solids or an aqueous solution. And they also don't describe reactions where gases are like forming liquids or forming solids. Because in a lot of chemical reactions, you get the evolution or the production of a gas. And the ideal gas law allows you to relate pressures, volumes, and temperatures for the gas along with a changing number of moles of gas. Like, for instance, when you drive a car or operate a piece of equipment that runs on gasoline or diesel fuel, there's a liquid fuel, and that changes into a gas. So you start out with a liquid fuel and oxygen, and that changes all into gases. The exhaust that comes out of the tailpipe of a vehicle is 100% gas, the gas state. So the number of moles increases. When you burn fuel, the pressure goes up, the volume goes up, the temperature goes up, and the number of moles of gas go up. There's a change to all those different values. All right, so PV equals nRT is the equation that you need to know. That's the ideal gas law equation. So here's some things about this ideal gas constant. And this, I guess you could say, is a little bit confusing. The ideal gas constant, R, it's the ideal gas constant. Like when you think of a constant in an algebraic equation, the idea of a constant in mathematics, it's a number that doesn't change. But the ideal gas constant has, for us, three different possible values: 0.0821, 62.4, or 8.31. And you might be like, well, how's it a constant if it has different values? Well, they're not really different values. They have different numbers in front depending upon what the pressure unit is. So do you see the first one says 0.0821 liter atmosphere per Kelvin mole or mole Kelvin. The other one is 62.4 millimeters of mercury times Kelvin mole. And the last one, 8.31, is kilopascal Kelvin mole. So it turns out that the different values are equivalent in their value whenever you consider what the unit is. So what I mean by that is, like, if I write 2 dozen, that is equal to like maybe 24 apples. So if I have 2 dozen apples, I've got 24 apples. The number changes from 2 to 24, and the unit changes from dozen to, an individual quantity like an apple. Here, the number changes, but so does the unit. And it's because the conversion factor to get from atmospheres to millimeters mercury and kilopascal, those are kind of built into the number itself. This 8.31, that is I guess you could say, the most standard, or the SI, the metric standard value for the ideal gas constant, because kilopascal is actually the most fundamental of the units, not atmospheres and millimeters of mercury. So I guess here's what I'm trying to tell you. Which value you use for the ideal gas constant depends upon what the unit for pressure is: atmosphere, millimeters of mercury, or kilopascal. So when you use the ideal gas law and you need the ideal gas constant, you just need to pick an appropriate value for the ideal gas constant. I'm going to actually, let me take a screenshot of that so I can like slide them over for the examples. All right, so here's an example of what I'm talking about. You got a cylinder with gas. It's got some kind of volume. It's got nitrogen gas in it. It's at some kind of pressure and some kind of temperature. I want to know how many moles of gas is in the cylinder. So the ideal gas law, PV equals nRT. I want to know how many moles. So how many moles, that's N. To get N by itself in the equation, you divide both sides by R and T. So N would equal PV over RT. It's important to have the values in appropriate units. So the pressure can be anything. This 200 kilopascal is okay. The pressure unit doesn't matter. But when I pick the value for the ideal gas constant, it has to have kilopascal in it. The value for volume is going to be in liters. We're just going to do everything in liters in this class. That's a nice standard for chemistry. In other fields, it's not necessarily the liter. The temperature has to be in Kelvin. So the thing about this list, like V, P, T, and R, is some of the values have to be in specific units. Other values can be in pretty much any unit you feel like. Let me show you. Let me do this. Screenshot. Okay, so the volume, 20 liters. I'm just going to write 20 liters by the volume. Hold on. 20 liters. And you see 20 liters, that unit, the liter, is in the values for the ideal gas constant. The ideal gas constant has units liter in all three of them. So liters is good. The pressure is 200 kilopascal, 200.0 kilopascal. So because the unit of pressure is the kilopascal, we're going to use this value for R, the 8.31 liter kilopascal per Kelvin mole. We would not use the other two because they have different pressure units, atmospheres and millimeters of mercury. So because this unit is kilopascal, I'm going to use the value 8.31 liter kilopascal per Kelvin mole. This is just the way the unit is written. It's not that you're substituting numbers in. The unit is liter kilopascal per Kelvin mole. The temperature is 27 degrees C, but you can't substitute a value in Celsius into the equation. There's two reasons for that. There are negative temperatures in Celsius, and if you were to put like a negative temperature in, it would give you a negative number of moles, which doesn't make any sense. It's like there's less than no gas. That's insane to say. And also, these temperatures in Celsius, if you go from like 20 to 40 Celsius, that looks like it's a doubling in temperature, but it really isn't a doubling in temperature. The Celsius scale doesn't start at a value of 0. It starts at negative values, and 0 is set at the freezing point of water. So for these temperatures, you must always add 273 to be able to get your temperatures in Kelvin. So that's 300 Kelvin. So the temperature must be in Kelvin. The volume must be in liters. The pressure can be anything, but the pressure units must match the units for R. So the units have to be liter for volume, have to be Kelvin for temperature, and then the pressure unit and the unit of pressure in R must match. Pressure units must match. That's a mess. I hate when that happens. Pressure units must match. All right, so you don't necessarily have to make a list of things, but making a list of things maybe helps keep yourself organized a little bit. In order to figure out how many moles, I'm just going to substitute the values: pressure, volume, R, and T. The pressure is 200 kilopascal, so N, we have 200 kilopascal. The volume in liters is good, 20 liters. R, the ideal gas constant, you want to pick a value for the ideal gas constant that has the same unit for pressure as the pressure unit. It's provided in the problem, 8.31 liter kilopascal per Kelvin mole. Liter kilopascal per Kelvin mole. And then the temperature has to be in Kelvin, so that's 300 Kelvin. So you see what happens here is a whole bunch of these units cancel out. And I know this is very complex with the units, but this kilopascal cancels this kilopascal. The liter in the numerator cancels this liter. This Kelvin cancels that Kelvin. And it leaves you with only the unit, the mole. And that mole is actually like in the denominator of a denominator, which just makes it like a straight up unit all by itself. You expect that the unit for N, the number of moles, is in the unit, the mole. So ultimately, the goal in dimensional analysis is to always make sure that all the units cancel out that need to cancel out. That's why when you pick the unit for pressure or unit for the ideal gas constant, it has to be in kilopascal so that unit cancels out the unit for pressure. Similarly, the temperature can't be in Celsius because Celsius wouldn't cancel out the Kelvin in R. So they both must be in Kelvin. There's no ideal gas constant values that are in Celsius. Let's see, 200. Yeah. Let's see, 220, 2.31. So it's like 1.60. I guess we have like, well, when you add 27 to 273, the 300 has three significant figures, so 1.60 moles is good. So in other words, I got a cylinder, and it's got some gas in it, and how many moles of gas happen to be in that cylinder depends upon the pressure, the volume, the temperature, and the number of moles. All right, that was a lot of stuff to walk through, like all the little different steps and stuff, but you get a hang of it as you do a bunch of them. So with this equation, you can figure out anything. You don't have to just figure out number of moles. You can figure out a pressure. You can figure out a volume. You can figure out a temperature. Or experimentally, if you measure pressure, volume, number of moles, and temperatures, you can confirm that the ideal gas constant is actually like 8.31 or 0.0821 liter atmosphere. So that one's a solution for a number of moles. You can convert a molar quantity into a mass. So for instance, this is 1.60 moles. We had 1.60 moles of nitrogen. Nitrogen is N2. So if you want to convert that into a mass in grams, let's see, I think yours has 14.0. Nitrogen gas. So nitrogen's molar mass is 14 point, I think it's just 14.0 on your periodic table. Let me see. Schoology, home, chemistry 1. Let's see, materials, reference. Because it's like 14.0067. Uh, 14.01. Oh, that's crazy. How'd that change that color? That's not even a color I get as an option. Oh, that's weird. That was like a zoom annotation. I can't get rid of that. All right, anyway, 14.01 grams per mole. I don't know what that's all about. I accidentally turned the zoom annotation on and now it's stuck on the screen. So anyway, N2 must have a mass of 28.02 grams per mole. So if I have 1.6 moles of nitrogen, then well, the molar mass is 28.02 grams per mole. 1.6 moles of nitrogen, you can convert that into a mass in grams because every mole of nitrogen has a mass of 28.02 grams. So I don't know, 28.02 times 1.6, 44.8. So here's the thing to know. Gases, you can't just weigh them. The air in this room has mass, but it isn't like you could put the air in this room in a box and put it on a balance and it pushes down on the balance because the air is neutrally buoyant within itself. You can't weigh out gases. Even if you were to put helium in a container, an empty box has a certain weight. If you put helium in it, it'll make the box buoyant. It'll make it so the box weighs less, even though you've put gas in it. So the issue with finding masses of gases is it's impossible to just throw it on a balance and find a mass. Instead, the goal is to relate the pressure, the volume, and the temperature of gas to a number of moles, and then you can convert that number of moles into a mass. And that's truly how much mass there is, despite the fact that you can't find it on a balance. So balances are only good for finding masses of liquids and solids generally. For gases, you got to use the ideal gas law to figure out relative quantities. That thing's still stuck on there. Let's see. How can I get rid of that? Annotate, eraser. There it goes. Get rid of it. Okay. So here's another example. I got some volume of methane. CH4 is methane. As you know, it's got one carbon, so the prefix is meth, and there's more than two times as many hydrogens as carbon, so it's an alkane, so that's methane. 2.24 times 10 to the 6 liters of methane. It's at a pressure of 150 kilopascal, temperature is 42 Celsius. how many moles and grams do you have? So there's the ideal gas law, PV equals nRT. The pressure is 150 kilopascal. The volume 2.24 times 10 to the 6 liters. The temperature is 42 degrees C, but you can't leave it in Celsius. You got to add 273 to it. So you're like 315 Kelvin. The value for R is whichever value R has an appropriate unit for the unit for pressure that's in the problem. So here's our choices of values R. This was in kilopascal. So again, we can use this 8.31. What's up? You're back. You're the second person to stop back from first period. Nick was here a couple minutes ago. Yeah. I think he was confused what class it was, though. He's like looking for a class that looks like his. All right, how many moles? All right, so number of moles is whatever PV over N or RT is. So you got a pressure 150 kilopascal. Volume, that's 2.2 million liters. The ideal gas constant you want to use is whichever one has a pressure unit that's the same as the pressure unit that you've measured. You know, here it's in kilopascal. It's like 8.31 liter kilopascal per Kelvin mole times the temperature. It's got to be in Kelvin, 315 Kelvin. So let's see, 150, 2.24 times 10 to the 6th, divided by 8.31, divided by 315. So there's only 3 significant figures here. So it's 128,000 moles. And if you want to know the mass in grams, well, the first thing you got to do is figure out the formula mass for methane. So you got 1 carbon, and I think it's 12.01 on your table. Yeah, 12.01. And you got 4 hydrogens. They're 1.01, so that's 4.04. You add those up, you know, it's 16.05. So the formula mass for methane is around 16.05. If you want to convert this number of moles into a mass in grams, you can take the 128,000 moles and 1 mole of methane has a mass of 16.05 grams. So that's like, well, you can write it in scientific notation. It's about 2 million grams, 2.06 times 10 to the 6th grams. And that's natural gas. You know, it's a pretty good volume of natural gas with a pretty good mass. That's, I don't know, 2,000 kilograms, which is like around 4,000 pounds, about 2 tons of methane. It's a fairly large quantity of methane. All right, so those are some simple examples. You have the other paper says like ideal gas law practice worksheet. Only 2 of the values for R are top. The most common units you run into are atmospheres and kilopascals. Millimeters of mercury is useful to meteorologists, but usually we're not talking about atmospheric gas. We're usually talking about gas like in a laboratory. So you maybe measure in atmospheres or kilopascal. So in this one, how many moles of gas does it take to occupy 120 liters, pressure of 2.3 atmospheres, temperature of 340 Kelvin? So the ideal gas law, start out as PV equals nRT. You can solve the equation for whichever variable you're looking for. How many moles is N? So N is equal to PV over RT. And then you can substitute the values. You just need to make sure that they're either in standard units or that the pressure unit matches the value for the ideal gas constant. So pressure can be in atmospheres. 2.3 atmospheres is okay. 2.3 atmospheres. The volume should be in liters, so I have 120 liters. The ideal gas constant is whichever value has a unit in it that's the same as the pressure unit. So because this is in atmospheres, the liter atmosphere per mole Kelvin is the value you want to use. That's 0.082, 0.082 liter atmosphere per mole Kelvin. It doesn't matter if it's Kelvin mole or mole Kelvin, either way is all right. Times the temperature. And this temperature is in Kelvin, 340 Kelvin, so that's good. It's important to notice that all the units will cancel out except for whichever unit you're solving for. Here are moles. So the unit atmospheres cancel, liters cancels, Kelvin cancels, left with the unit, the mole. And you just do the math. 2.3 times 120 divided by 0.082 and 340. A good way to judge how many significant figures there should be is to look to see how many significant figures are in each of the values you're working with. 120 only has 2 significant figures. That 0 at the end is not really significant. The 2.3 has 2, and the 340 has only 2. That 0 is not considered to be significant. So with 2 significant figures, looks like 9.9 moles. Let's see, I can copy this. That didn't do what I wanted it to do. I'm doing something here. Let me fix this. I wonder if I can, I can't do that. Oh, that's weird. Document. Huh. It's not what I was expecting. To this. All right, so the second one, you don't have to use the equation to solve for a number of moles. You can solve for just about anything. So number 2, the basic equation is that PV equals nRT. You could solve for pressure, you could solve for volume, solve for number of moles, solve for temperature. So number 2, I have a 50-liter container. It's got 4.5 moles of gas at 200 degrees Celsius. What is the pressure? So if you know the volume, number of moles, and temperature, you can figure out what P is. So to get P by itself, you just divide both sides by V. So it turns out the pressure of a gas is equal to nRT over P or over V. So N, a number of moles, 4.5 moles. So I can be like 4.5 moles. Now, R, well, you're not given a value for the pressure. So it turns out that whichever value you pick for the ideal gas constant will give you a value for pressure, and the unit for that pressure will be in whatever unit happens to be in the ideal gas constants unit. So I'll show you this in a couple different ways. If I pick this value up here, 0.082 liter atmosphere per mole Kelvin, 0.082 liter atmosphere per mole Kelvin, times the temperature, so 200 degrees C, that's the same as 473 Kelvin, and divide by the volume, 50 liters. That gets you a value for pressure, and because the pressure units mole cancel, Kelvin cancel, and liter cancel, atmosphere is a unit for pressure. This answer will come out to be in the unit atmospheres. So let's see, 4.5 times 0.082 times 473 divided by 50. There are only two significant figures because the 4.5 has only two significant figures. This 200 has probably got more than two, but 3.5 atmosphere. If instead you decide to use the other value, 4.5 moles times 8.31 liter kilopascal per mole Kelvin, then you see moles cancel still, Kelvin still cancels, liters cancels, and it leaves you the unit of kilopascal. So whatever this comes out to be, we'll just have the unit kilopascal, and it'll be exactly equivalent. So 4.5 times 8.31 times 473 divided by 50, it's like 350. Now 3.5 atmospheres and 350 kilopascal, those are equivalent. They're the same. And to prove that, with two significant figures, just to show you, if you convert from atmospheres into kilopascal, 1 atmosphere is the same as 101.3 kilopascal. Now, it's not going to be exactly 350, but to two significant figures, yeah, it's 350. Like with two significant figures, it's 350 kilopascal. So you see that if you use a ideal gas constant that's in atmospheres, you get an answer in atmospheres. If you use an ideal gas constant with kilopascals in it, you get kilopascal. And 3.5 atmospheres is the same as 350 kilopascal. So if it's not defined what the pressure unit for the answer has to be, you can use any pressure unit or any ideal gas constant unit you want, and the answers will be equivalent to each other. It's just the same as like saying, you know, like you could say 300 years or you could say 3 centuries. They're the same amount of time. It doesn't make any difference at all. All right. You can try the third one at the bottom. We'll go over the third one at the bottom tomorrow, and then I've got some more practice that we'll do in class tomorrow.
I mean, like, I feel like she doesn't. I don't think she expects you to finish it. She's waiting on what.